Hey everyone, in this video we're going to review Rolle's theorem and the mean value theorem and do some examples. So Rolle's theorem essentially says if you have a function that satisfies the following three hypotheses, then we have the conclusion. So the things that Rolle's theorem has to satisfy is that f is continuous on the closed interval ab, f is differentiable on the open interval ab, and that f of a equals f of b. So if those three are satisfied, then Rolle's theorem guarantees the existence of a number c such that f prime of c is equal to 0. So essentially what this means is that if you have a continuous function, usually I start with this, if your f of a equals f of b, right, you have two y values that are the same and the function is continuous, then there has to be a point where you're going to have a horizontal tangent line. A picture like this comes to mind. So you have A and B, and these are not the same, right? A is different than B. And so maybe I should say here with A not equal to B. And then the y values are the same. So in order, if you have a continuous function that moves from point A to point B, and they have the same y value, then at some point that function has to have a point where it goes up and then it has to come down. So that point, there's going to be some value c where the line is horizontal. So the slope is 0, which means the derivative is 0. And it doesn't have to be like this, right? It could be the other way. It could be upside down. It could be on the negatives. So there's a number of ways that we could make this graph. But really what we're focusing on is that if f of a and f of b are the same, then, right, the function, whatever the function is doing, so here it's increasing, decreasing, and it's doing stuff, as long as it's continuous and differentiable, meaning the derivative exists everywhere between a and b, then in this one, notice that we actually have quite a few c's. So it doesn't have to be just one. Rolle's theorem guarantees the existence of one c. There could be more. So like in this case, I have this function and you have a and b, and f of a equals f of b. So notice that we have a horizontal tangent line there. We have a horizontal tangent line there. And we have a horizontal tangent line there. So these are all places where the derivative is 0. So what Rolle's theorem says is essentially if you have a continuous function and differentiable on an interval, then and f of a equals f of b, so the y values of the endpoints are the same, then at some point, right, the function has to have a horizontal tangent line because it's either going up and then coming down. Like in this case, it's going up and coming down to reach the same y value. So then that change, where it changes from going up to going down, you have a horizontal tangent line. And then in this case, here in this little valley, right, it's going down and then it goes up. And so we have a horizontal tangent line there. And in order for us to say that the derivative is 0, that's why we need the fact that f is differentiable on the open interval AB, so no cusps and no discontinuities. But mainly this is saying the continuous already tells us, right, there's no jumps or asymptotes or discontinuities. The differentiable part tells us there are no cusps, because remember, if you have a cusp, then the function is not differentiable. So we want to make sure that everywhere the derivative exists, and so if the derivative exists everywhere and you have the situation where you're going up and then down, then at that point the derivative is going to be 0. You're going to have a horizontal tangent line. So let's try an example. Let's try this example. Verify Rolle's theorem for f of x equals x plus 1 over x on an interval 1/2, 2. Then find the value of c guaranteed by Rolle's theorem. Alright, so that means to verify Rolle's theorem, we have to verify the three conditions. That the function is continuous on the closed interval, that is differentiable on the open interval, and that f of a equals f of b. So first of all, is it continuous on the closed interval 1/2, 2? So f of x looks like it is not continuous where? So this is not continuous at x equals 0, right? Because at x equals 0, you have 1 over 0, so you have a vertical asymptote here. But 0 is not on our interval. Is it continuous everywhere else? Yeah, that's the only place where the function is not continuous, right? So, but 0 is not in our interval 1/2, 2. And so therefore we can say f of x is continuous on the closed interval 1/2, 2. Now, is it differentiable on the open interval 1/2, 2? So let's look at the derivative. F prime of x is, what is this? F of x is x plus x to the minus 1, so we can use the general power rule. So it'll be 1 minus, bring the minus 1 down, x to the minus 2, so minus 1 over x squared is the derivative. And this, so we want the derivative to exist everywhere on the open interval 1/2, 2, and this looks like it exists everywhere except at 0. So this is not defined at x equals 0, but again, 0 is not in our interval, in the open interval 1/2, 2. So therefore we can say we can say that f of x is differentiable. And the derivative is defined. Differentiable on the open interval 1/2, 2. And so now, so we have the first and the second condition. So the first condition is that f is continuous on the closed interval. The second is that it is differentiable on the open interval. The third is that f of a equals f of b. So our interval is 1/2, 2. So on the interval 1/2, 2, we can say a appears to be 1/2 and b is 2. So f of x, let me just rewrite it, is x plus 1 over x. So therefore, what is f of a? F of a will be f of 1/2, which is, let's see, x plus 1 over x. So 1/2 plus 1 over 1/2. So this is really 1/2 plus 2, which is 2.5. And what about f of b? F of b is f of 2, which will be 2 plus 1 over 2, which is still 2.5. So it meets the three conditions of Rolle's theorem. Is continuous on the closed interval 1/2, 2. It is differentiable on the open interval 1/2, 2, and f of 1/2 equals f of 2. And so we can say by Rolle's theorem, there exists a c, so there's a value of c in the open interval 1/2, 2, such that f prime of c is equal to 0. Now the second part, it says, what did it say? Verify Rolle's theorem for the function on that interval. Once it's verified, then find the value of c guaranteed by Rolle's theorem. So f prime of c by Rolle's theorem we know is equal to 0, but we also know f prime of x is, what was it, 1 minus 1 over x squared. So that means that f prime of c is equal to 1 minus 1 over c squared. So you have two things, right? You have f prime of c is equal to 0, and you have f prime of c equals 1 minus 1 over c squared. So f prime of c is one thing, but f prime of c is the other thing, so those two things must be the same. So we can say 1 minus 1 over c squared has to be 0, and then solve for c. So 1 equals 1 over c squared, cross multiply, so c squared equals 1. Take the square root of both sides, so c equals plus or minus 1. Don't forget the plus or minus. And we're in the interval 1/2, 2, so we're only going to take the one where that fits in the interval. So c equals 1 is in the interval 1/2, 2. So that means that c equal to 1 is the value guaranteed by Rolle's theorem. So that's where you're going to have a horizontal tangent line. Let's try another example. So let f of x be tangent of x. Show that f of 0 equals f of pi, but there is no number c in the interval 0 pi such that f prime of z equals 0. So essentially saying it contradicts Rolle's theorem. So why does it contradict Rolle's theorem? So let's take a look at that. First, show that f of 0 is equal to f of pi, and that we can just do by plugging in values, right? Our f of x equals tangent x, so that means that f of 0 is going to be tangent of 0, which is 0, and f of pi is tangent of pi, which is also 0. So those are the same. So that means we have shown, right, that f of 0 equals f of pi. But why does it contradict Rolle's theorem? Why can't we say there is no number c so that the derivative is 0? Well, Rolle's theorem says that the function has to be continuous in the closed interval and differentiable in the open interval. So on 0 pi, is f of x equals tangent x continuous? What do we think? No, right? Notice that f of x, tangent x is sine x over cosine x. And so this tangent is not continuous whenever cosine is 0. And cosine is 0 at pi over 2 and every multiple of pi over 2. And pi over 2 happens to be in the interval 0 to pi. So f of x is not continuous on the interval 0 pi, so we can't use Rolle's theorem. So Rolle's theorem does not apply. So we have to have a continuous function in a closed interval, differentiable in the open interval, and f of a equals f of b. So just because f of a equals f of b, that does not guarantee the existence of a c where the derivative is 0. So the other two conditions, all three conditions have to be satisfied in order for us to be able to use Rolle's theorem. The next theorem is the mean value theorem, which the mean value theorem tells us that if f is continuous on the closed interval ab, so very similar to Rolle's theorem, and f is differentiable on the open interval ab, then there's a number c in ab such that the derivative is equal to the change in y over the change in x. So notice that this says, what does this really say? F prime of c, right? The derivative, we know that this is the derivative, the slope of a tangent line. So this is the slope of a tangent line at x equals c. And what is f of b minus f of a over b minus a? Right, that's change in y over the change in x. So this is slope also, but the slope of what? It's not of a tangent line. This is the slope of the secant line that connects the 2 points. Connecting a, f of a, and b, f of b. So let me draw a picture of that. So bear with my graph over here. So you have AB, you have your A f of A, B f of B, and so this black line is the secant line. And the red line is the tangent line. So the mean value theorem essentially says that when you have any secant line that connects 2 points in a function, if your function is continuous in the closed interval and differentiable in the open interval, then there's a point on that interval where the tangent line at that point is parallel to the secant line connecting those 2 points, right? So then that's meaning the slopes are the same. So the lines are parallel. So that's really what it's telling you. And so I kind of want you to look at Rolle's theorem, the graph, the first graph that I had shown you. So here, notice that you have f of a equals f of b. And then, so if you're staring at this, tilt your head to, say, the left. So if you tilt your head sideways to the left, you'll get this graph. And so I oftentimes think of the mean value theorem as really Rolle's theorem on the side. So if you were to then imagine rotating this then 90 degrees, so, or if you rotate it so that is parallel to the x-axis, you're going to have Rolle's theorem. So Rolle's theorem is what promotes the mean value theorem. So what forms the mean value theorem? Can't think of the word that I'm trying to use here. All right, so then that is the mean value theorem. Pretty big concept here. Only two conditions: f of x is continuous on the closed interval AB and is differentiable on the open interval AB. So you have to have a continuous function on the closed interval, and the function then has to be differentiable. Remember, differentiable means that derivative exists on that interval. So let's try an example where we verify the mean value theorem. So let's try this example. Verify the mean value theorem for this function on the closed interval 0, 4. And once you verified it, find the value of c guaranteed by the mean value theorem. So first of all, we have to make sure that the function is continuous on the closed interval. Notice that f of x is a polynomial, so that means that is going to be continuous everywhere. So my abbreviation for continuous is CTS, so it's continuous on the entire real line, so therefore it's going to be continuous on the closed interval, so on 0, 4. What about differentiable? F prime of x is equal to 3x squared minus 2x. So is this defined everywhere? Or are there any places where it's undefined? No, right? So this is going to be defined everywhere. So that means the derivative exists everywhere. So then it exists on the interval 0, 4. So therefore we can say f of x is differentiable, right? Differentiable means the derivative exists. So we're just looking for, is this undefined anywhere? So this is differentiable on the open interval 0, 4. So we have that is continuous on the closed interval, is differentiable on the open interval. Therefore, by the mean value theorem, there is a c in the interval 0, 4 such that f prime of c is equal to what? So f prime of c equals f of b minus f of a over b minus a. So f of 4, right, b minus f of 0, f of a over b minus a. So over 4 minus 0. And so that is what the mean value theorem tells us. So as long as you can prove that it's continuous on the closed interval, so you have to make that statement, somehow show that your function is continuous on the closed interval, that the derivative exists everywhere on the open interval, then we can say then there's a point c, a number c inside that interval, where the derivative, right, the slope of the tangent line is going to be equal to the slope of the secant line that connects the 2 points. So what does this look like? For the next part, we want to find the c. So find the value of c guaranteed by the mean value theorem. I have my derivative over here. F prime is 3x squared minus 2x. So f prime of c is going to be then 3c squared minus 2c, right? F prime of c, f prime of x, just replace every x with c, equals f of 4. So let's find the value of f of 4. So plug it into where? This is f of 4, not f prime of 4. So I'm going to go back to the original function, x cubed minus x squared, and plug in 4 there. And so what do we get when we do 4 cubed minus 4 squared? So that's going to be 4 cubed minus 4 squared minus f of 0, which is 0 cubed minus 0 squared, over 4. And so do that out. So I get 3c squared minus 2c equals, what does that equal? 4 cubed is 64 minus 16 is, what's that, 48, and then divided by 4. So you're going to get 12. And now we want to solve for c. So how do you solve for c here? Set it equal to 0. Essentially you have a quadratic and you want to solve for the variable. So 2c minus 12 equals 0. Does it factor? I'm not sure if it factors, so we can just use the quadratic formula. So c is going to be the opposite of b. So we have it equal to 0. Okay, so a is 3, b is negative 2, and c is 12. So the opposite of b, so 2 plus or minus the square root of b squared, so 4 minus 4ac all over 2a. And then figure that out. And so that's going to give us the c that we want, and then we just choose the one that is inside the interval 0, 4. So let's see, 2 plus or minus the square root of 4, and minus times a minus becomes plus, and then 4 times 3, and then times 12, which is really 12 times 12, which is 144 all over 6. And so 2 plus or minus, what's that? A square root of 148 over 6. Be careful not to say, oh, that's 2 and 12. You don't take the square root over addition. So then from here you can find the values. And so I'm going to use my calculator to approximate it, and I'm going to choose the one that is between 0 and 4. So one of the values of c is negative 1.694. Well, that's not in the interval 0, 4, so probably not that one. And the other one is 2.361, rounding to 3 decimal places. So we're going to choose the one that is in the interval 0, 4. So this will be the value of c, guaranteed by the mean value theorem, will be 2.361. Alright, so I have a couple more examples to cover, but I'm going to record a new video for that. So we'll call that part 2 of the mean value theorem. And so go on to part 2.